Okay, here we go. So we're now talking about the rate determining step. If we look at a reaction mechanism I hope you're familiar with, so just a standard nucleophilic substitution of bromoethane the OH minus comes in, attacks. Remember the arrow, curly arrow shows the movement of a pair of electrons attacking from the OH minus, attacking the carbon, attacking that carbon there. Why? Because it's got a tiny or partial positive charge from the electronegative bromine there. So if I was to do an experiment where I collected rate data, then we would determine that let's say I'm using sodium hydroxide, the rate is first order with respect to bromoethane and first order with respect to NaOH. Sometimes we talk about the total rate order. Total rate order is just all of the rate orders added up. So if it's first order with respect to bromoethane and first order with respect to sodium hydroxide, the total rate order is 2. I don't think I mentioned that before. Anyway, okay, so that's all fine and dandy. If I now take a different chemical, and react that with sodium hydroxide, do the same thing. We'll do a nucleophilic substitution at that central carbon there. There we go. That's just the overall balanced reaction there. And then I look at the rate data for that reaction. C4H9 will have to do there. It's first order with respect to the bromine, the alkyl bromide, but sodium hydroxide doesn't turn up in the rate equation. Or another way of saying is that it's zero order with respect to sodium hydroxide. Changing the concentration of sodium hydroxide makes no difference. Well, why is this? Well, this gives us a bit of an insight into the mechanism here. We know that hydroxide and the alkyl bromide are both involved in this reaction because the concentration affects the rate. But here, the fact that the concentration of the sodium hydroxide doesn't affect the rate of the reaction tells us that it's not involved in that all-important first step. So what we have here is 2 steps for the reaction. In step 1, our bromine thingy here spontaneously breaks down to make a carbocation there. Is that stable? Well, the carbocation is stabled by a little bit of positive inductive effect. These methyl groups can push along a little bit of electron density and make that stable. But it would probably be a reversible reaction, and either way that process is slow. And then once we've made that, well, now if there should be a hydroxide around, now that would swoop in and occupy that carbon there. Okay, and that happens pretty fast. So we've got two steps of the mechanism: a slow step, which is a bond breaking step, you'd expect that to be slow, and then a bond making step you'd expect to be fast there. The reason it goes in this order rather than the traditional OH minus coming in and attacking the carbon is that we've got three kind of big groups here in a tetrahedral fashion, all boxed in around that carbon, and bromine's a pretty big atom as well. So it's actually just difficult for the OH minus to get in there. It's difficult for it to attack. The term for that is steric hindrance. I don't think that's on the syllabus, but it's a nice bit of wordage. Okay. The lesson here is that step one, being slow, is let's just put this down here, the rate determining step. In other words, the speed of the whole reaction is determined by how fast this first step goes. And you see that in life. You see that in instances where you've got a chain of things that have to happen, but the rate at which we can get all of those things done depends on the slowest step. And we often see this when you're washing up after a big dinner. If you've still got a person sitting at the sink, you might have lots of people clearing plates from the table, and lots of people drying up with dishcloths in their hands. But if there's only one person stood at the sink washing the plates, then the rate at which the whole process can be completed depends on how fast that person is washing the dishes. Okay, so let's look at a different example here. An imaginary one. It means we're just working with letters of the alphabet rather than big complicated formulae. Okay, here's our reaction here, and here are the steps that reaction follows. So in the first step, A and B get together and form a kind of an AB thing. They sort of join together. And in step two, AB and another B get together and form an AB2. That wasn't there. And that's the slow step there. And then step three, our AB2 meets up with a C, and then they run off and make a D and E. And that happens fast. So the important step is this slow step. Well, what we see here is that A is used before the rate determining step. That's that one, rate determining step. A is in the reaction before the rate determining step. So that means that A will definitely be in the rate equation, probably first order. C appears after the rate determining step. There's no C's in step 1 or 2. It only appears after the rate determining step. So C will not appear in the rate equation, or if it does, it would be written to a 0 power. Well, what about B? Well, B definitely appears in and before the rate determining step. But notice that we need two B's. B appears here and then it appears again there. So this is that situation in which B would be second order. So just to summarize those rules there, if it's in the rate equation, A, B or C, whatever it is, if it's in the rate equation, it must appear in or before the rate determining step. If it's in the rate equation and second order, well then it must appear twice, in or before the rate determining step. And then lastly, if it's not in the rate equation, it cannot appear in or before the rate determining step. Just to summarize that again. So A appears in or before the rate determining step, so it's in the rate equation. B appears twice in and before the rate determining step, so it's second order in the rate equation. C appears after the rate determining step, therefore plays no part in the rate equation or appears zero order.